Chapter 3 is all about 95% confidence intervals. And the game plan is to go through 4 different scenarios. So in the first scenario, we'll estimate the 95% confidence interval on a single population mean when the standard deviation of that population is known. And then we'll move on to a situation where we're trying to get a 95% confidence interval on the difference between 2 population means when population standard deviations are known. Then we'll move on to drawing inferences, getting a 95% confidence interval on a single population mean when sigma is unknown and estimated by the sample standard deviation. And finally, 95% confidence interval on the difference between 2 population means when sigma is unknown and estimated by the sample standard deviation. And so what this video is going to focus on is this second scenario. And again, ultimately, what we're really concerned with is this sort of situation. Excuse me. Now, what I want to do is I want to begin with some notation. So what we're interested in is U2 minus mu1, the difference in population means between 2 populations. And the way we're going to estimate that is we're going to take a sample from the second population and determine the sample mean for that, and sample from the first population, determine its sample mean, and the difference, that's going to be our estimate of the difference between those 2 population means. Now, there's a lot of things going on here, so I'm not going to use, in terms of notation, I'm not going to use this very often. Instead, I'm going to represent the difference between the population means as theta and our estimate of the difference between the population means derived from our sample means as theta hat. And so this thing here, that's known as a hat, and it's very common notation to use when we're making estimations. Now, recall that throughout the videos, at least up until now, I've been making a really big deal about the difference between what we get when we actually do the experiment, the one particular time we do the experiment, as opposed to the set of all possible outcomes that might have happened when we do the experiment, the random variable. So, for example, we made a big deal about the difference between lowercase y and uppercase y, between lowercase y bar, uppercase y bar, and we did our confidence intervals. We talked about the lower limit and the upper limit versus the lower limit and the upper limit. Now, in this case, so we make this big distinction between what we get when we do the experiment, when we do our experiment, our one experiment, shown here, and the set of all possible outcomes which we consider to be our random variable. And the idea is we have different symbols here than here. And the point that I want to make is that in this section, theta and theta hat, we're not going to make a distinction in terms of notation. So there's no difference in symbols between our one observation and set of all possible observations, the random variable. But hopefully you'll be able to figure that out from the context. Okay, now what I want to do is go on and look at figure 5 in your notes. So this is figure 5 from your notes, and it's going to be used to determine how we actually figure out the difference between 2 population means. So here we're going to have our first population right here. A is population 2. And population 2 is normally distributed with mean mu2 and standard deviation sigma. And then population 1 is normally distributed with mean mu1 and standard deviation sigma. And the thing about our standard deviation sigma is that it's assumed to be the same for both populations, and it's also assumed that we know what it is. So, what are we going to do? We're going to go out there and we're going to get our first value of theta hat by taking a sample from the second population, getting its mean, sample from the first population, getting its mean. Once we've got this value of theta, we can put it on the number line. And then we can repeat that process. So if we were to do it again, we might get, almost certainly we would get different values for y1 bar and y2 bar, get a different number, and we get that point on a number line. And we would repeat this an infinite number of times. So if we would repeat this an infinite number of times, what would we get? Well, what we would get would be a probability density function. So we get a probability density function, and there it is. Now, because it's the probability density function of a sample statistic, and remember our sample statistic here is theta hat, our estimator of theta, we can think of this as being a sampling distribution. So, what are the features of this sampling distribution? What are the features of this sampling distribution? I'm not going to show them. Is that this sampling distribution, if we consider the set of all possible values of theta hat that we could get by infinitely repeating the process of getting a sample mean from the first population, a sample mean from the second population, and taking the difference. If we consider that sampling distribution, although I'm not going to prove it, first of all, it's normal. Secondly, the mean of all possible theta hats, all possible values of our estimator, is going to equal theta, the true difference between the two population means. And because it's a normal distribution, it's going to have a standard deviation. And the standard deviation is going to be sigma squared over the number of observations taken when we took our second sample plus sigma squared divided by the number of observations in our first sample. This is a sampling distribution. This sampling distribution has a standard deviation. We use the term standard error to refer to standard deviation of a normally distributed sampling distribution. So that's figure 5. And now what I want to do is review. I go with figure 4. And figure 4 is in your notes. And what it's meant to show was how we got the 95% confidence interval on a single mean. So this is just pure review. So remember, we assumed that our underlying population was normally distributed with mean mu and standard deviation sigma. And then what we figured out was that if we took all possible samples, we can represent those as a random variable y bar. They would also have a normal distribution with the same mean as the underlying population, but with a smaller standard deviation, because the big observations and the small observations are going to tend to average out, have a standard deviation of sigma over root n. And then you do a bit of algebra and say, okay, what we can do is take that formula, subtract the mean, divide by sigma root n, and that gives us a standard normal distribution. And the whole idea of a standard normal distribution is that once we've got a standard normal distribution, we can use our z-table. So we go to our z-table and find out that we can have a z value is equal to 1.96, and that's going to form the basis for making a 95% confidence interval. And so we've got this P here, and perhaps I should have expanded that out. This P means probability. The probability, once we know that this is true, once we know that y bar minus mu is normally distributed with a standard normal distribution, and our z value from the z table is 1.96, we can come up with this relationship, that the probability of this random variable, y bar minus mu divided by sigma root n, the probability of it being greater than minus 1.96 and also less than positive 1.96, that's going to be equal to 0.95. And then we did a little bit of dancing around the inequality sign and showed that this is true, that y bar minus 1.96 times sigma over root n less than or equal to mu less than or equal y bar plus 1.96 times sigma divided by the root n, but the probability of this being true was equal to 0.95. And then we did something that would help in generalization to more or less generalize. We said, okay, this 1.96 is relevant for a 95% confidence interval. If we wanted to generate, let's say, a 90% confidence interval or a 99% confidence interval, instead of using 1.96, we'd use the appropriate z value from the z table as z alpha over 2. And this sigma over root n, that's the standard error. That's the standard deviation of the sampling distribution. And so once we got this equation, we can almost draw a line here and say that we know that this is all mathematically true. But everything up until now has been based on this y bar, or y, all capital letters, all dealing with random variables. But then we go out in this last step when we actually do our experiment. So now we're getting lowercase y bar. We calculate this. This is our 95% confidence interval. And we did a whole bunch of chatter about what this actually meant and what it didn't mean. So now what I want to do is think about this, having just reviewed the way that it works when we're trying to get a 95% confidence interval on the mean of a single population. How is this game going to be played when we're trying to get a 95% confidence interval on the difference between two populations? So it's very similar to what we saw before. So what we have is theta hat is normally distributed with mean theta and standard deviation that I'm going to represent as SE. And that's what this is all about. That's what this is all about. We consider all possible values we might get of our estimator theta hat, every possible value of y2 bar minus y1 bar, and we decided that would be normally distributed. It'd have a mean equal to the true difference between the two populations, and it would have a standard deviation that would be equal to this. But since this thing here is a sampling distribution, we can refer to our standard deviation as a standard error. So that's what this is saying, that instead of all possible estimators of the difference between two means is normally distributed with mean that is equal to the true difference in population means and a standard error that's given like this. So once we got this relationship, just as we did before, we can do a bunch of algebra and we can say that theta hat minus theta divided by the standard error is going to have the standard deviation. Then we go to our Z table and find that the appropriate Z table for a 95% confidence interval is equal to 1.96. And once we've got that, we just repeat the process that we use when we're trying to draw inferences around a single mean and say, okay, the probability that this thing here lying between minus 1.96 and positive 1.96 is going to be 0.95. And then we just danced around the inequality sign to get this relationship. And so what we came up with is the probability that theta hat plus or minus 1.96 times the standard error, the probability that straddling theta is equal to 0.95. So with all that in mind, let's go back and let's do an example. So now we're going to do an example. We've got population 2 and population 1. And we're going to assume that they have the same standard deviation, which is equal to 15, which means they have the same variance, which is equal to 15 squared, or 225. And again, this is pretty unrealistic, but remember, we're just going through a process, and ultimately we're going to compare the means between two populations where sigma is unknown. But for the time being, we're going to assume, rather unrealistically, that we know what sigma is. So then we go out and we do our sampling. So from population 2, we do a sample of size n equals 25, and our estimate of y bar 2 is 110. And then from population number 1, we take a sample size of 9, and we calculate the mean for that sample, and we get y bar 1 is equal to 100. So the plan is to get a 95% confidence interval on theta hat, which is going to be y2 bar minus y1 bar, which is going to be equal to 10. So we want to get a 95% confidence interval on our estimate of the difference between those two means. So again, just as a review and help put things in perspective, think about what we did when we wanted to get a 95% confidence interval on a single mean. How did we do that? What we did was we took y bar plus or minus z alpha over 2 over the standard error. And that's kind of the generalized formula that uses z as opposed to as a general term, as opposed to any particular value of z. So now what we're going to do is do a very similar thing, except now because we're interested in the difference between two population means, we're going to use theta hat. And what we're going to do is we're going to calculate theta hat plus z alpha over 2 times the standard error. So the whole thing that I want to do here is point out the parallelism between what we did earlier when interested in drawing a 95% confidence interval on a single mean, and the difference when we're trying to draw a 95% confidence interval around the difference between two means. There really isn't that much difference between these two processes, because in both cases, it's going to be the appropriate z value multiplied by the appropriate standard error. So let's think about our situation. What do we got here? Well, what's theta hat? It's equal to 110 minus 100, which is equal to 10. What's z? Alpha over 2, 95% confidence interval, so it's 1.96. What's our standard error? What's our standard error? As you recall, the standard error is going to be the square root of sigma squared over n2 plus sigma squared over n1, and that's going to be equal to the square root of 225 over 25 plus 225 over 9, and that's all going to turn out to be 5.83. So having those values in hand, we just plug those in our equation, and what we get is our 95% confidence interval goes from minus 1.4 to 21.4. And again, it's 95% confidence interval on the difference between mu2 and mu1, which we represent as theta. What does this mean? What does it doesn't mean? Recall, concept of a 95% confidence interval, what we cannot say. We cannot say that there's a 95% probability that the mean lies between these two values. That's because the mean isn't a random variable, the mean is fixed. Nor can we say that there's a 95% probability that these two numbers straddle the mean, because once we've done the experiment, these two values are now fixed. We can't really speak of probability. What we can say is either one of two things have happened. Either these particular values straddle the mean, or they don't straddle the mean. But this last thing would be a rare event, and since we generally don't believe in rare events, we're going to accept that these two values straddle the true mean, and we'll use that as the basis of telling the story in our thesis or publication. So stop there.